Okay, this is the second part of the graphs of sine and cosine. We saw from the last video that graph of y equals sine x looks something like this, and y equals cosine x looks something like this. In this video, we'll start to look at some of the special characteristics and some of the functions that correspond to the different graphs. So I'm first going to only speak on sine of x, but everything that we discover in the graph of sine is applicable to cosine. So first thing we notice is if I went along the graph of sine to x, there will be a point at which the graph starts to repeat itself. If I started at a different place, went along the graph, again, there would be a point at which the graph would start to repeat. When this occurs, that means we have something called a periodic function. It's a function that repeats its values at regular intervals. Additionally, one complete repetition of the pattern, that's called a cycle. So when I went from here back to 0, that was one cycle. So whenever it starts to repeat, that's when you've completed a cycle. Additionally, this type of function is also called sinusoidal. A sinusoidal function is nice, a smooth, repetitive oscillation, meaning the graph is oscillating back and forth between the values -1 and +1 in this case. So this is considered a sinusoidal function. Additionally, therefore, both sine and cosine are actually sinusoidal functions. We notice then, if we look at the distance between the 2 points in between any particular cycle, that's actually called a period. The period is literally the horizontal length of one complete cycle. The period in this particular graph, which is the graph of our parent function y equals sine x, the period of sine is 2 pi. Similarly with cosine, the period for the graph of y equals cosine x is also 2 pi, meaning it takes a distance, a horizontal distance of 2 pi. So if I started here at 0, I would go all the way to 2 pi before it starts to repeat. This does not say it repeats at 2 pi. It says I would go a distance. So if I started at -pi, I'd have to go all the way to +pi before the graph starts to repeat. The distance between -pi and +pi is a distance of 2 pi. Similarly, if I started at -2 pi, I would have to go all the way to 0 before it starts to repeat. The distance between -2 pi and 0 is 2 pi. So again, period is simply how far you have to go before it starts to repeat. Some other characteristics. We notice that it oscillates up and down between 1 and -1. There is, I guess, a line of symmetry, if you will, even though it's not a line of symmetry. This line is called the midline. The highest point is a maximum, while the lowest point is called the minimum. So these are just some of the characteristics that every graph of y equals sine x has. If we expanded these lines, the distance between the midline and the maximum is called the amplitude. The distance between the midline to the minimum is also the amplitude. So again, the amplitude is simply the vertical distance from the midline to either the maximum or the minimum. I did want to speak on two other aspects of the graph of sine of x. I wanted to speak about the domain. The domain again tells you how far left and how far right the graph goes. Well, graph of sine of x continues forever to the left and forever to the right. So the domain would be all real numbers, or in interval notation, -infinity to +infinity. If we consider the range, range is how far up, how far down. The highest it goes is 1, the lowest it goes is -1. So the range would go from -1 to +1. And notice how it's written. It's inside of the brackets. The brackets is an indication that you actually can include these values, whereas the parentheses says you do not include the infinities. Okay, so what we're going to look now at is the general form of the sinusoidal functions. This is the general form. Y equals A sine times bx minus c plus d. I know it looks like a lot, but let's consider some of our previous functions we've studied. We first studied linear functions, and in linear functions, it also had variables. We learned that each variable was a particular characteristic of the graph. We learned that the m was the slope and the b was the y-intercept. When we got to quadratics, the quadratic equation in vertex form is written y equals a times x minus h quantity squared plus k. As we studied that quadratic in this form, we saw that each of the different variables had represented a certain characteristic of our graph, specifically the parabola. We learned that the A impacted the let us know something about the vertex. It let us know if the vertex was a maximum or a minimum, meaning if A was negative or if A was positive, let you know how the parabola opened. The H and the K were the coordinates for your vertex. You saw that the H wound up being your x coordinate, while the K was your y coordinate. Now, if I put the vertex form right next to the general form, you'll see the similarities that they have. They both have a coefficient out in front. They both seem to have things grouped inside the parentheses, and they both have a constant on the outside. So I'd like to bring your attention to the different variables we're going to be working with, the A, the B, the C, and the D. And I want to boil it down to something really general. The A happens to be a coefficient, which means we're multiplying on the outside of the parentheses, while the B happens to be a coefficient on the inside. The C is a constant term on the inside, while the D is a constant term on the outside. It's just to help organize the different variables to consider. So you've got four variables. Two of them are coefficients, two of them are constants. One of them is on the outside, one of them is on the inside of parentheses. So what we're going to do now is take our general form and begin to discover what each of the different variables will tell us about the graph. So we'll start with what I have here is an actual graph of sine of theta, or sine of x. And you notice the function that I have here is actually in the general form. And this is the typical equation, the graph you saw we created when we first drew y equals sine x. Right now you can see that the first coefficient outside the parentheses is 1. The coefficient on the inside is 1. The constant, both constants, are 0. And these are our identity values. So this is the parent function. So as I begin to change the values for each one of the different variables, we'll discover how it impacts the graph. So I'll start with A. As A increases, I notice that the height increases, or better yet, the amplitude increases. As A goes up, so does the amplitude, meaning the distance between the midline and the max, or the midline and the min. So just from this simple discovery, we can see that the A impacts the amplitude. Now, if I made my A negative, you should have expected that it begins to reflect. But now notice, if I made my A negative 3, the distance between the midline and the amplitude and the max is still a distance of 3. The negative tells us it reflects. The 3 just lets us know how far to travel from the midline to the max and from the midline to the min. So that's our A. I'll put it back at 1. There we go. Now let's look at B. I'm going to jump to D because D's a little easier to see. All right. As I move my D, it's simply moving up and down, up and down. So it's D right now is 2. I know, oh, look at that. That means my midline is at 2. If I come down to -2, I'm getting close. There we go. My midline is at -2. So right now we discover that the A represents our amplitude. The D is simply our midline. So I'll put it back at 0. We'll now play with the B. As I change B, looks like you might think it's getting skinnier or something to that effect. What's happening is we're changing how far we have to go before it starts to repeat, which is our period. So if I changed it, let's put it to 2 to see what happens. So when I change B, come on, let's get there. Almost there. We are 2. When I change it to 2, and let's compare. Normally, it would take a distance of 2 pi before it starts to repeat. Now it's a distance of only 1 pi. So it looks like as B goes up, the period goes down. So it's kind of counterintuitive. Right now, the period is pi. The original period was 2 pi. So if I took this 2 pi and divided by 2, I would get a single pi. So that tells me I can find my new period by taking the original 2 pi and dividing it by b. Let's see if I took it to 0.5, then I can see, oops, that's 1.5, sorry. Almost there, 0.5. Now, if I went from -2 pi, I'd have to go all the way to 2 pi before it starts to repeat. So b got smaller, but the period got much larger. So if I took my original 2 pi and then divided it by 1/2, I would actually get the 4. For the purposes of this video, I'm not going to put a lot of emphasis on C, but I'll just illustrate what happens with C. C just makes it move left and right. But what it does not do, it doesn't change our midline, our amplitude, things of that nature. In another video, we'll discover how to deal with the C. So we'll go back to the PowerPoint. And so what we discovered is that A is our amplitude, and we're going to take the absolute value. So even if it was negative, the amplitude is a distance. Okay? If the A was negative, that just lets us know it reflected. Then I jump to the D. D was our midline. And because it's a midline, we have to give it in the form of an equation. It's a horizontal line, y equals d. Next thing we saw was that B impacted the period. And what we had to do was a simple formula. 2 pi, which is the original period, and if we divide it by B, that gives us our new period. So the maximum was simply the midline plus the amplitude, and the minimum, so the simple formula, if I took my midline, D, and added the absolute value, that'll get me my maximum. My minimum, do just the opposite and subtract. In the next video, I'll do a few examples to illustrate how we can find maximum, min, midline, amplitude, etc.